So it's our pleasure to have here today Hao-Jui Kuan, who is
Yes.
a PhD student at the Tübingen University in Germany under the supervision of Professor Costas Kokotas, and also a PhD student at National Tsing Hua University in Taiwan.
Yes. Yeah. Okay.
Hao-Jui is going to talk about G-mode resonances as triggers for precursors of SGRBs. So please, Hao-Jui.
Okay. And thank you for the introduction. Yes. And in today's talk, we are examining the possibility of the G-mode resonances as the triggers for the precursors in the short gamma ray burst events. So first of all, let's see this cartoon diagram of this scenario where we see that when these two star binary and the binary system is barren with each other, then the tidal field of the companion would exert some tidal force that perturbing on the primary star. And this tidal force, typically the leading effect of this tidal force has the frequency twice as the orbital frequency. And if the frequency of the perturbing force matched to the frequency of some certain quasi-normal mode of the star, then this mode would be resonantly excited. And because that any quasi-normal mode, the stellar oscillation will will cause some stress and therefore some strain on the crust. And this strain and stress, the strength of this strain scales as the amplitude of the mode. So if this mode eventually excited to exceed some certain extent, then the strain that caused by this mode would be possible to exceed the threshold that the crust can respond linearly to, which means that when the strain beyond this critical value is realized during the resonances, then the crust is possible to melt. And over the region where the crust failure happens, the energy previously stored in this region would be released in some form. And supposing all of this energy released release it in the magnetic field radiation, then this may cause the precursor event before the short gamma ray burst, which often occur after the merger by around 100 milliseconds. So in this case, and in this scenario, we are suggesting, and later we will state why we suggest that a G mode is relevant for this kind of crustal failure. Okay, and then first of all, let's see what is the short gamma ray burst and what is the precursor of it, and how can we see them in the light curves. And all the observed gamma ray bursts can be categorized by the timescale T90, which is defined as the time interval during which 90% of the photon count has been detected for a given gamma ray burst. And this timescale T90 for all the observed gamma ray bursts has this bimodal distribution as shown in this figure on the right-hand side. And the two peaks here indicates that the gamma ray burst may have may be possible to group into two classes. And one is defined by T90 is smaller than the T90, the timescale T90 is less than 2 seconds, and the other one is defined otherwise. And because that a rigorous way to classify a gamma ray burst should take into account the central engine of that event, which means that one should consider also other accompanying observations which are related to the central engine as well. So this would make things much complicated to then define a given event is a short one or a long one. However, the T90 criterion is a commonly used in the literature. So in this work, we stick to this definition for short gamma ray burst. So as we see in this particular event, GRB 090510, we see the huge peak, the highest peak on the by the right edge. This means represents the short gamma ray burst after the merger, while preceding this huge peak, there are two smaller peaks before this main episode. And these two peaks are identified as precursors of this given event. And the time separation between the peak to the smaller peak to the main burst is called the waiting time of this precursor. Okay? And as the uncertainty in the identification of a short gamma ray burst, there are some uncertainties in clarifying or in identifying a precursor event, because that this pre-emissions always much fainter than the main burst. So the visibility of this kind of precursors is not as good as the main burst. So to detect them, may thus biased by the energy band that designed for the apparatus. Also, there in literature, some authors would require that the waiting time of a precursor should be larger than the should be larger than the T90 timescale for the short gamma ray burst itself. But however, and in this work, we do not impose this constraint in identification of a precursor event, and we collect some most significant event in this table, where we can see that on the first in the first column, we record the event, the short gamma ray event for this precursor, and at the third column is the waiting time for this given precursor event, where we see most of them precede the main burst by roughly 1 second. However, there are some of them occur even earlier. For example, this 4 events highlighted in green have the waiting time a few seconds before the merger, before the main episode. And in particular, there is one event marked in orange. This event precedes the short gamma ray burst by more than 10 seconds. Okay. And at the final column of this table, we listed the orbital frequency at the time the precursor occurs, which means that most of the precursor event is expected to occur when this orbital frequency is around 600 Hertz, while these 4 green events happens when the orbital frequency is around 300 Hertz, and the most peculiar one event happens when the orbital frequency equals to is less than 200 Hertz. Take into account the relation between the perturbing force and the orbital frequency in the bottom left, and also the relation between the perturbing force and the gravitational force that corresponding to the orbital frequency. Okay, we can see that the perturbing force corresponding to this precursor event is around 100 Hertz. It is a few hundred Hertz. Sorry, a few hundred Hertz. This hints that the mode, the stellar oscillation mode, that may be relevant for this event should be G mode. If there is no interface between the crust and the core of the neutron star. So in this talk, or in our 2 papers about this project, we ignore we do not consider interface between the crust and the core, so that we don't have this shear mode, and the interface mode has the also the few hundred hertz. So only the possibility for our case is the G mode that can be relevant for this event. Okay, so in calculating the orbital evolution, we take into account the third order up to third order post-Newtonian effects, and the gravitational wave back reaction have been dealt with 2.5 post-Newtonian order scheme. And apart from these two pointwise orbital effects, we consider the tidal effect by these the last two pieces of the Hamiltonian. One of them, the H tide, is the tidal potential, is the tidal energy that gained by the primary from the tidal field of the companion, where we know that this tidal energy is dominated by the leading order, the leading order term of the potential, which has the spherical harmonic number L equals to 2 equals to m. And the other part of this tidal effect is describes the dynamics of the quasi-normal mode of the star, which has this the harmonic-like Hamiltonian, where this Kc denotes the time-dependent displacement of the matter. And it is because that the mode, the Kc caused the stress on the crust, so that the mode would distort the star, more or less. Okay, so taking into account all these four pieces of Hamiltonian, we can solve for the evolution of the binary, and also then consider certain tidal effects, the leading order tidal effects into the evolution, where we plot this this solid curve, the blue solid curve, as the orbital frequency, and in some sense the orbital frequency as the function of time. I translate this orbital frequency into the corresponding gravitational wave frequency as the axis, and the y-axis is the time with respect to the burst. The TB is the time of the short gamma ray burst. And in this plot, I also summarize the events that and the event in the aforementioned table, where we see that now we can see clearly that most of these precursor events occurs at the time when the gravitational wave frequency is around 100 seconds to 200 seconds. And one of these, the blue point on the top right, top left, this corresponds to the second precursor event of that peculiar short gamma ray burst 090510. And this event corresponds to a slower gravitational wave frequency because the waiting time of this event is much longer than the others. Okay, and now in this blue curve for the orbital evolution, we only consider the F-mode effect into this line, while we will involve the G-mode effect into the orbital frequency as well, into the orbital evolution as well. However, we know that even we can take into account G-mode in the simulation, this blue curve would not be changed that much. Actually, the changes in the blue curve would be negligible because that the coupling of the G mode to the orbital evolution is much smaller than F mode, where we see that by this plot we demonstrate that the coupling between the mode, how the strength of the coupling between the mode and orbit would alter the evolution of the binary system. For example, and the typical magnitude of the coupling strength for F mode is Q equals to 0.1, which is plotted in red. And we see that if we take into account the F mode, when it compares to the case, there is no tidal effect. The light blue curve, we see that there is a significant difference between these two evolution. However, as we go to smaller strengths of the coupling term, the Q, when it goes down to 0.01, which is the purple line, basically there is no measurable difference between the no tide case and this tidal effect. Okay. So because that the F mode typically has this Q number smaller, even smaller than this 5 times 10 to the -3, which is the green line. So we conclude that even if we include the G mode effect into the orbital frequency, this blue line, this blue curve on the right panel on the right figure would not be altered that much. So basically, all the events would still lie on this curve. Okay, and the G mode of this of a star is restored by the force, the bionic force, and this bionic force can be parameterized by the ratio between the adiabatic index for the equilibrium and the adiabatics for the perturbation. And in particular, if we denote the capital gamma as the adiabatics index for the perturbation, and this small gamma represents the adiabatics index for the equilibrium. If these two gamma do not match to each other, then there is the non-trivial ratio here defined by 1 plus delta. So if this delta doesn't equals to 0, then the Bayes force would generate would reveal the G mode spectrum of the stellar oscillation. And the stability of this kind of G mode, this kind of the stellar oscillation G modes can be determined by the this Schwarzschild discriminant A. And if this A function is positive, then the G mode of this star would be stable. On the other hand, if the A is negative, then the G mode would be unstable. In this case, we are considering the stable G modes. Therefore, we would constrain our delta to be positive number, so that this A would be positive as well. Okay, and in this figure, we are showing the eigenfunction of first 5 G modes, where we see that for the G1 mode, the blue curve, there is no knot inside the star. However, when it goes to higher order, the knot would increase by 1 when we go to 1 higher overtone of G modes. Okay. And this G mode would be perturbed by tidal force, as stated in the first cartoon diagram. And if the perturbing force has the frequency matched to this frequency of the G mode, then the G mode will undergo an resonant time scale, during which the mode amplitude would increase rapidly, as shown in this figure. We see that the resonance happens at this yellow line and ends at this purple line. Before and after the resonance, the mode amplitude would oscillate around a constant. However, during this resonant timescale, the mode amplitude would increase rapidly. And to determine when is the resonance occur for G modes, we have to take into account all other perturbing force, which will shift the G mode frequency. accordingly. For example, in this work, we will consider the centrifugal and tidal and Lorentz force that act on G modes causing some certain shift in their frequency. Okay, and this frequency modification can be calculated by the equation on the bottom right, where we see that the perturbing force delta F has the couples to the eigenfunction of the mode Kc, and this coupling between the eigenfunction, the displacement of the matter caused by that mode, and the perturbing force leads to this correction in frequency. So in particular, we are considering the dipolar magnetic field in the neutron star. And when a neutron star is born in violent circumstances, for example, as the remnant of a supernova explosion, the newborn neutron star may have a multipolar magnetic field. However, most of the overtime component is unstable. So during the evolution, during the neutron star growing old, all of those higher order components were dissipated away and collapse into the dipolar magnetic field. So for the neutron star in the binary system, which are typically very old, it's most likely that the magnetic field on those neutron star has the dipolar structure. Okay, so the explicit form of the magnetic field is the first line represented here, where we see that at the toroidal component, which is the phi component of this B4 vector, the toroidal part of this magnetic field is controlled by the parameter lambda defined in the second equation here. And when this lambda equals 1, which means that this magnetic field do not have any toroidal component, and thus this magnetic field is purely poloidal. However, when this lambda goes to smaller and smaller number, then the toroidal component would be more and more dominant. Okay. And from this magnetic field, the perturbation onto this field would generate the Lorentz force, which can be expressed by this long equation. And on the other hand, we are considering a slow and uniform rotation on the star, which then generates the centrifugal forces, which can be expressed at this three equation on the bottom, where the omega alpha is the free mode frequency, and the capital omega is the stellar rotating rate that we are considering. And the m here is the Whiting number of the quasi-normal mode that is altered by the perturbing force. Okay, so taking into account these two perturbing force on the spectrum, for the magnetic field, the shift in frequency can be plotted in these two figures for G1 and G2 mode, and for certain stellar model. At the x-axis is the shift, and at y-axis is the shift, and the x-axis is the component, the ratio between the toroidal and the poloidal component. And let me remind you that when this gamma equals to 1, which is the right-hand side of these figures, then the toroidal part would be weakened. However, when this gamma goes to the left, the toroidal component would be strengthened. Okay, so for a given characteristic, or say for a given poloidal component of the magnetic field, when this lambda go to approaching 0, then the total magnetic strength would be increased, because that we are fixing the poloidal component, but you increase you keep increase the toroidal component. This will lead to higher and higher magnetic strength. So there is the local viral limit on the field strength, which says that locally the strength of the magnetic field cannot exceed some certain value at the order of 10 to the 18 Gauss. So by virtue of this limit, we can place a lower limit or the lower bound for this gamma parameter, which is plotted in as the black solid line in these two figures. And there is some numerical simulation as well as the analytical stability analytics about the configuration of the magnetic field. And this literature suggests that there is a range of lambda such that the magnetic field can be stabilized so that it would not be dissipated in some way. And this stabilization range for the gamma is plotted as the green area here. So we see that the viable region of the viable values for this lambda is the green area right to the black line. Okay? And over this viable region, we can see that there is a subset of the lambda where for which the shift for G1 mode is negative while it is positive for G2 mode. This tells us that the G1 mode frequency in this range of lambda would be shifted downward. However, the G2 mode frequency would be shifted upward. And in the extreme cases, actually it's not that extreme. When the magnetic field and strength falls into certain range, the G2 mode frequency can be even higher than the G1 mode frequency. This is interesting because typically if there is no any other perturbing force on the spectrum, on the stellar spectrum, the G1 mode frequency is always higher than G2 mode frequency. It's the kind of definition of G1 and G2 mode. However, when we consider certain perturbing force into the star, then we can make G2 mode frequency higher than G1 mode frequency. This will lead to this plot where we show in the waiting time of the G1 mode resonance and also the waiting time for G2 mode resonance in yellow and in blue curve, the solid yellow, solid green, solid yellow and solid green curves respectively, where we see that when the magnetic field strength go to higher level, then the shift for the G1 mode would bring its frequency approaching zero. And when it very close to zero, then the instability of G mode would be triggered. And showing by the dashed yellow line here is the strain that caused by G1 mode. And in this dashed yellow line, we also can see that the instability would be triggered if the strength of the magnetic field is higher than a certain level. Okay, and in this curve, the horizontal purple line here is the criterion that we use to test if the strain by the mode if the strain by the mode strong enough such that the crust would melt, and where we see that the G1 mode can lead to this kind of crustal failure only with strong enough magnetic field strength, while for G2 mode the case is on the opposite. Up to certain level of the magnetic field, all of the G2 mode can lead to a crustal failure. So this plot suggests that G2 mode may be more relevant in this scenario, this tidal-driven crustal failure scenario. Okay, and on top of the magnetic field effect into the spectrum, the uniform rotation also shift the frequency according to this relation on the right. We see that the m here is the Whiting number again, the omega here is the rotating rate, and the coefficient c is the number that would be numerically determined, and this c number, this coefficient, is dependent on which mode you are talking about. For example, for G1 mode, we plot this c number in the top panel, and for G2 mode, we plot it in the bottom panel, where we can see that the value for this c coefficient is actually not so different for these two modes. And the G1 mode has the value around 0.105, and the G2 mode has the value around 0.11. So the difference between the value for G1 and G2 mode is actually not that big. And this is also true for F mode, as shown in this figure. We are talking about the F mode frequency as the y-axis, and the stellar rotation as the the F mode frequency is the y-axis, and the stellar rotation is the x-axis. And here, because we are talking about a slowly rotating star, so we are focusing on the segment of the curve close to the y-axis. And during this, by observing the part of the curve nearby the y-axis, we can see that the uniform relation between the overtone of F mode, where the red curve is for L equals to 2 F mode, and dashed blue is for L equals 3, and the green is for L equals to 4. And the C coefficient that we talked about is basically the slope of the curve. And when we are talking, and when we focus on the slow rotating limit, then the slope of the curve is almost the constant for all the overtime considered in here. So for G mode and for F mode, we also we see this universality of this C coefficient for higher order quasi-normal mode. And besides of this observation, we also see that this gamma, we also see that the C coefficient do not depend on the stratification, which is the ratio between the adiabatics for the equilibrium and the adiabatics index for the perturbation, which is defined by the 1 plus delta in previously. And this delta, when this delta varies, the C coefficient in principle would be changed as well. However, we are showing here that we observe in our results that the variation in the delta in the stratification of the star do not change the C coefficient much, and this is shown in this figure on the left hand side, where the gamma 1 here is basically the delta defined in our context. And we see that for a different value of the gamma 1, again, the slope corresponds to the C coefficient. So, and when we focusing on the slow rotation limit, all of these curves have the same slope, which means that the C coefficient for different stratification is most likely the same. Okay. So taking into account the rotation and the magnetic field perturbation into the spectrum, we can determine the G mode frequency, and then we match this G mode frequency to the perturbing force frequency. Then we can get we can determine the onset of the resonance. And but before we can say something conclusive about this scenario, we have also to check the region of the crust over which the crustal failure may occur, even when we have a strong enough strain. For example, that we carry out the strain configuration for G1 mode and for G2 mode, which are the left panel and the right panel. And we see that the configuration of the strain of these two modes is stronger, is the strongest in the equatorial region. And one more thing we can observe is that the G2 mode can generate stronger strain on the crust. And this strain defined by the stress tensor in the left block. And the right block shows that this strain is actually proportional to the mode amplitude of the G1 and G2 mode we are talking about. And when this denoting the maximal value of the strain over the whole crustal region as the sigma max, we see in the color bar here the sigma max for G1 mode is roughly 0.018, while the sigma max for G2 mode is 0.06. And this okay. To test if the mode can actually cause the crustal failure, we can look on this. We can compare this sigma max with the von Mises criterion, which is the threshold number of the crustal strain over which the crust material would not be able to respond linearly to the distortion. Okay, and but however, there is some uncertainties in determining this von Mises threshold. Some literature would use 0.01 as their criterion, but some literature use the 0.1 as their von Mises threshold. However, if we adopt the lower bound of if the lower value of this von Mises criterion, in this figure we are showing that the sigma max for several models and also with several equation of state, and the dashed line, the bottom lower dashed line represents the lower value that have been used as the von Mises criterion. However, the upper curve is the larger criterion that have been used in some literature. Okay. And if we look at this lower look at this lower threshold, one conclusion that one can draw is that two of them may, three of them is much likely to bear a crustal failure on their surface, which are the equation of state FF1, FF2, and WFF1, WFF2, and APR4. However, for the other two, SL1 and WFF3, an equation of state, the generated sigma max is by and large less than the other three equation of state. So if we adopt the higher value of the von Mises threshold, these two equation of state may no longer not be able to predict such precursor event. And one more thing that we can observe from this figure is that the sigma max is larger for the stellar model with higher or smaller compactness, while for the model with medium size of the compactness, it's not as likely as the other models to generate such crustal failure. And the implication of this observation is that because that in a binary system, it's unlikely that both star has small compactness and both star have high compactness. It always comes as like as a huge one and another one is smaller than the other. So this figure, then this plot suggests that the mergers, the binary systems that is favored in this scenario, in this tidal-driven resonances scenario, would be those having a symmetry mass ratio. Okay, which means that if we are considering the binary systems with the same chirp mass as shown in, for example, the chirp mass of the level, the same as GW170817, the vertical blue line here, we can see that at the same and with the same chirp mass, the mass ratio is higher or the mass ratio is smaller, the sigma max would be stronger with relative to the other cases. So that the binary system having large q and small q would be favored in this obstacle and this electromagnetic observation. However, when we talk about the observation via gravitational wave, this kind of system would suppress the measurability of the gravitational wave, because that although it's not showing here, that the phase shift in the gravitational waveform is actually scaled as the q to the -5. So for the very large q, or for and here we define that the smaller mass, the smaller one, I can say, we define the q. Okay, if we constrain that the primary be the lighter one, the companion be the heavier one, then the mass ratio between the companion to the primary would larger than 1 by definition. And in this definition, the measurability of the phase shift in the gravitational waveform scale as q to the -5, which means that the more asymmetric of the system is, the less measurability of the gravitational waveform shift, the phase shift. Okay, so this is on the opposite of the electromagnetic field observation. Okay. And also we explore the relation, the dependence of this sigma max on the rotating rate nu here, and the rotating rate and the y-axis here, and the toroidal component of the magnetic field. And we see that at the the most left panel, when the magnetic field, the characteristic magnetic field strength equals to 8 times 10 to the 14 Gauss, and the stratification equals to 0.005. This dependence of this sigma max on the two parameters basically is the same as the case with a bit smaller magnetic field. So the pattern would be would be altered a little bit, but generically speaking, they are the same pattern. And we see that for these two cases, only the different the stratification is the same. Only the magnetic field strength is different, but the sigma max predicted in these two cases is the same, which is around 0.07. And I'm talking about the value when the maximum value of this sigma max can get by varying the rotating rate and the lambda here. However, if we consider a larger stratification as shown in the right panel, where the delta equals to 0.01, we can see that in this case, the sigma max is at the same level. However, it can be realized with broadened region, the broadened more combination of this stellar rotation and toroidal component ratio. Okay. So there is showing the dependence of this sigma max on these parameters. And going back to the observed precursors to see if our scenario can fit against all of this event. And in this event, as we stated above, that the G2 mode is more likely to produce this kind of crustal failure. So in this table, we are using the G2 mode resonances as the triggers for these precursors, and we are considering one rotating case. Also, and the toroidal component have been fixed to be lambda equals to 0.18, which is a very large component of the very large toroidal component with respect to the toroidal component is very large with relatively to the poloidal component. And we vary the strength of the magnetic field to find a fit between the occurring time of the precursor and the occurring time of the resonance of G2 mode. And we find a fit for all of these events apart from the GRB 090510B, which is the earliest precursor that we have ever observed. And because of this large waiting time of 13 seconds, it's not possible to just use magnetic field to shift the G2 mode down to that small value. So in this case, we use the same magnetic field strength as the 090510A event, but we add some rotation into this B event. However, the rotation that is required to find the fit between the onset of the precursor and onset of the resonance is around 70 Hertz, which means that this progenitor, this neutron star, spin down from 70 Hertz to 0 Hertz within a space of 13 seconds. This is a very, very, very fast accelerate of the neutron star, and therefore the tension raised by this strong spin down can be alleviated if we also consider some rotation when the A event have occurs. However, there is also another scenario that can account for these two events of only one short gamma ray burst, which is by G1 mode by using G1 mode to explain this B event. So as we stated above, that for the certain range of the lambda and certain level of the magnetic field strength, we can make G1 mode frequency lower than G2 mode frequency. Then if we exploit this this influence of the magnetic field, we can actually make the G1 mode resonance at the time when the B event, this 090510B event occurs, while the G2 mode frequency matched to the 010510A event. So there have been proposed two possible scenarios to account for two precursor events, but only one short gamma ray burst host. Okay, and this scenario can also be used to constrain the equation of state, as shown above, that three of the equation of state can generate a larger sigma max, while the rest two of them, the SLY and the WFF3 equation of state OS, and generate the smaller number on the of the sigma max. So if we obtained the precursor event from some from a neutron star of a given compactness, we may use this information to set some constraint on the equation of state. And also, if these two events of the gamma ray burst 090510 are actually accommodated by G1 and G2 modes, which means that we can use one short gamma ray burst event to obtain the information about the eigenfrequencies of two modes. And this will lead to a strong constraint on the equation of state, because that we are showing in this table and this relation, the universal relation between the G1 mode with respect to the as a function of the stratification, and the fitting parameter stigma is listed in the table, and we can see that the fitting parameter of this relation is different for each of these five equation of state. So if we and actually the G2 mode obey the same relations and obey the same fitting coefficients. So if we can obtain G1 and G2 mode of a given neutron star simultaneously, then we can leave a very strong constraint on the equation of state. Okay, so the takeout of these two papers is that the information about the equation of state from this precursor event, if the tidal-driven crustal failure scenario is really the mechanism behind of these pre-emissions, then this would shed some light on the dynamics of binaries when the gravitational wave frequency is around 100 Hertz. And this knowledge about the gravitational from the gravitational wave is actually independent message of the this information about the dynamics of the binary at this stage is actually independent message of the gravitational wave with the ground-based detectors. Yeah, so that's for today's talk.
Okay, so let's first of all turn on our microphones and our videos to acknowledge Hao-Jui Kuan for his seminar.